First, I would like to show off our multi-sim simulation. We can see that I have my flip-flop followed by 4 counters and then the shift registers. Simulate the encoder inputs. We use 2 function generators in multi-sim plus an oscilloscope to take a look at what's inside. We used an XOR gate to double the amount of pulses. We chose not to implement the XOR gate in the breadboard because we found that the encoder from our motor actually output a ton of pulses, which will quickly overflow our counters. The next thing you should notice is that we have our indicator LEDs. They will light up based on if the bit goes up. And on the output, we have an oscilloscope that is supposed to help us look at what the output of the shift registers look like. In order to read what we have in the shift register, we had to have a signal which will give the shift registers the load or the shift signal low or high. And we already have an external clock which would have output all 16 bits by clocking up and down. And you can see that in our simulation right now, it would go up and down according to what the bits look like from most significant to least significant. Next, at the top of the schematic, we have an input for our reset for the counter, except right now we preloaded some value already into the counter. You should be seeing high, low, high, low, high, low, high, low, 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 high, low, high, low, high, low, from most significant to least significant. The next thing I will do is just toggle the shift and load signal from the bottom right there, and you should be able to see on the oscilloscope it goes like high, low, as indicated by the LEDs. And once more to make it very clear. Transitioning into our next part, we have our motor hooked up to our counter circuit. So you should be able to see from the least significant bit up here to the most significant bit down here that the motor is incrementing because I'm putting it clockwise, which is our positive direction that we have chosen. And you can see that right now the counter is overflowing quite a bit, even at 9 volts, but we will deal with that later in code. Next, I swapped the polarity of the motor, so now it will be turning counterclockwise, and we should be able to see that our counters are going backwards. After this, we'll show you what it looks like when it's connected to the Arduino, as you can see right on the right side. Next, I'm going to show you that our Arduino program is reading 0 because we just resetted our counter over here. And the motor is not running, so everything is just still. Next, I will just turn on the motor at around 3 volts, so it's a bit slower, so you can see the counters again counting up. So now we see everything is turning and turning, and if we take a look at our Arduino program, we have all our values coming in and also the overflows to show how many times we actually overflowed our counters. Notice we also have our angle calculation there, and it seems to just be increasing and increasing because we're just going around and around. Earlier I mentioned that we had a reset, so this is showing off the reset now before we move on to our next portion. We have a button that would mimic what the microcontroller will give us, and pressing that button will reset our counters to 0. As you can see, that's what happened. And after that, I'm just going to run the motor at a slower speed to show you that it still works counting up even after being reset. For this section for the missed pulses, I don't actually have any video because we were really in the midst of testing using a logic analyzer we didn't have a ton of time with. But using the logic analyzer, we were testing out the 2 outputs of the encoder, channel A and channel B. We see that they have 4.028 times 10 to the 6, but then for here on channel B, it's 4.18 times 10 to the 6. So we're missing about 20,000 pulses. However, this was run at originally 12 volts for the motor, but even at 0.2 volts, as we can see on these next 2 images, there is still a large discrepancy that we can't get rid of. Transitioning to Altium, we have a schematic that I just copied from when we did multisim. So as you can see, we still have our flip-flop, our 4 counters, and 2 shift registers. But also we have these ports on this side, which will be connected to our second schematic, where we are interfacing with the STM32 microcontroller. We also have pin headers that will connect to the other portions of our project. So the last thing that I'm going to show you is our PCB design. For right now, we have our top layer here. You can see we have our microcontroller, our 2 shift registers, the flip-flop, and the 4 counters all placed on the design, and some pin headers on the side, of course, and we have our bottom layer as well. So everything is all connected, all the traces are there. We had to use some vias. So that's it for the proof of concept video. I hope that everything was clear, and I'll speak with you soon. Goodbye.